The lab activity today is on Newton's third law. And Newton's third law says when any two objects are in contact, the magnitude of the contact force is the same on each of them, and the direction is opposite. And that can be a pretty confusing concept. One of the most surprising concepts in Physics 1. And so today I want to, sort of point out how this works and get you used to how collisions are going to affect the bodies involved based on the mass of the objects. Okay, so here's kind of the thing that's confusing about Newton's third law. So say you have a collision between these two football players. This one is big. Put some clothes on this guy. And then he's colliding with, like, say, the punter, some much smaller person. He looks determined, though. Okay, so what's going to happen when these two players collide? There's going to be a major difference in the effect this has on the two players. The big football player is going to keep moving forward basically the way they were before the collision. The smaller player is going to go flying back the way he came, and so that's what makes it hard to wrap your head around the fact that it's sort of natural to think that the bigger player is applying a larger magnitude force to the smaller player than vice versa. Well, let's look at free body diagrams of these two players and then think about Newton's second law, and that's sort of going to clear up how this works. So a free body diagram of the bigger player. Let's see. I'm not going to get too carried away with this outline. Okay, so here comes the bigger player flying in. And there is a weight force. Let's say the player has a mass of big M, so there's going to be a weight force like that. And there's going to be a normal force. I'm going to ignore any kind of friction stuff going on. So we're going to think of both of these two forces as vertical. And then there's going to be one horizontal force. That's the contact force. So this is the force R that's applied to the big player by the small player. Okay, and now let's look at the free body diagram of the smaller player. They look sort of the same size here, but this person is has much less mass than the person on the left. So there's a weight force. That's the smaller mass, little m, times g. And there's a normal force from the ground. I'll call that N2. And now for our purposes, the thing that's important is this contact force, the force that's applied by the bigger player. And that force has the same magnitude R. That's the thing that's sort of hard to wrap your head around. Okay, so now if we want to understand why there's such a difference in effect that this force has on the two players, we have to go to Newton's second law. And so let's think about the horizontal, think of like the X component of Newton's second law for these two players. And I'm going to ignore the directions for now. But okay, so for the big player, Newton's second law in the X direction says R is equal to big M times A1. Okay. And so the horizontal acceleration of the big player is going to be R over big M. Now let's think about Newton's second law for the smaller player. Again, I'm ignoring the directions, but R is equal to, this time, the smaller mass times the acceleration of the smaller player. And so that A2 is equal to R over little m. Well, if you take this same magnitude force R and divide it by a bigger number, you get a small acceleration for the larger player. Okay, that's what happens when the denominator is big in a fraction, right? If you take that same number R and divide it by a smaller number, you get a big acceleration for the smaller player. And so you can see that even though those contact forces are the same, there are going to be major differences in the accelerations of the two players, and those accelerations depend on the mass of the player. Something with a big mass is going to have a small acceleration from this collision. Something with a small mass is going to have a big acceleration. And basically, this lab is just going to ask you to do that over and over again to recognize this and sort of solidify it in your brain. So in a collision, the small mass has a big acceleration. The large mass has a small acceleration. And you're just going to be asked that in a few different scenarios, kind of over and over again, to solidify that idea. One thing that I want you to really pay attention to as you do this stuff is there are two totally different kinds of diagrams that I'm going to ask you to draw. And you've seen these kind of diagrams before. I just want you to be really clear to yourself about what you're drawing as you do these diagrams. The first one doesn't have a name, but we've seen this before. Let's see. Do I know how to select on this? Yes. Okay, so let me take this guy and put it down here. Okay. So when you're doing this first type of diagram, the way you're thinking about this is like you draw a velocity, and then you think, okay, this person is slowing down from this collision, and so the acceleration parallel is this way. The person isn't turning, so you know that the total acceleration is also this way. And from Newton's second law, you know that the net force is the same direction as the acceleration. So your net force is that way. Okay, you've done these diagrams a lot. And if you also have a perpendicular part of the acceleration that goes with the object turning, then you know that you have a range of possible directions for the acceleration and the net force. The other type of diagram is a free body diagram. And this doesn't have any of these things on it. Okay, it doesn't have velocity, acceleration, net force. All it has on it is individual forces. So a free body diagram only has, in this case, the weight, the normal force, the contact force. there are no items that overlap between these two diagram types. You don't have individual forces on this first type of diagram. You do on the free body diagram. And you don't have net force or acceleration or velocity in a free body diagram. Okay, so be very clear to yourself about which type of diagram you're dealing with in each case. At the end of this lab worksheet, there are two questions, one about arm wrestling and one about tug of war. These are kind of, in a way, sort of brain teasers that can be kind of confusing. So in arm wrestling, you have these two arms. They're in contact up at the hands. And each person is trying to flatten the other person's arm down. And so this is another case where it's sort of natural to think, okay, the winner applies a bigger contact force to the loser than vice versa. But that's not how it works. You know that's not how it works because of Newton's third law. So let's think about the free body diagrams of the two forearms. Okay, so these are the two people. And Newton's third law says that these contact forces are the same. Okay, there's nothing you can do about that. In every case, when two things are in contact, those contact forces have the same magnitude in opposite direction. So then how is it that anyone can ever win at arm wrestling if in every instance, at every instant, the contact force is the same? Well, the answer is there are other forces acting on the forearm. And I'm going to sort of simplify it. This is, it's a little more complicated than this. But basically, you have forces down here that have to counteract that reaction force. And these forces, F1 and F2, are coming from the muscles of the arm. And so as that contact force increases, as these two people are pushing harder on each other, it's always the same magnitude force on each arm. But eventually you get to a point where the muscles in the arm of one of these two people are not strong enough to counteract that contact force. And when that happens, the person's arm accelerates backwards. And so it really isn't a story of which contact force is bigger. It's a story of whose muscles are capable of counteracting a bigger contact force. Okay, with tug of war, it's sort of the same story. So, here are the two people. Okay. Well, you might think the winner is the person that applies a bigger cable tension to the other person. But again, because of Newton's third law, that's not possible. So what's going on here? So let's think about the two free body diagrams. On this person, there is a weight force. There's a normal force. There's a friction force from the ground. And then there's a cable force. And on this person, There's a, possibly different weight, different normal force, different friction force. You could, whoops. You could give these subscripts because they're not necessarily the same. But the important thing here is the cable force is exactly the same on each of these two people. So the winner does not apply a bigger cable force than the loser does. So how can anyone ever win at tug of war? Again, it's the same story. You can think of it as kind of like misdirection. It's not about the cable force you apply. It's about being able to counteract the cable force that's sort of mutually applied. So with your muscles and your body position, you can affect how much friction force you can have acting on your body. And the winner is the person that continues to have this counteracting friction force that's sufficient to make up for the cable force that's mutually applied. So again, the winner doesn't apply a bigger cable force on the loser. It has to do with how the other things involved are capable of counteracting that cable force. Okay, one last thing I want to say. So this is going to ask you to do a bunch of diagrams of these two different types. Remember, so sometimes it's going to ask you to do them when the two things are at a distance from each other. Sometimes it's going to ask you to do them when the two things are in contact. Remember that even when the two things are in contact, you're going to do separate diagrams for the two things. So if two carts are in contact with each other and you draw your free body diagram of the whole system, it's going to be confusing because you're not going to have the contact forces in there at all. Instead, you need to draw individual free body diagrams of the two objects when they're in contact. So like in this example here, you can see that these two are in contact at this instant because there's the contact force, but I've drawn totally separate free body diagrams of the two bodies. Okay. Well, good luck, and let me know if you have any questions.